cylindrical and quadric surfaces. What are those? Well, we're going to start reviewing a couple of surfaces and their corresponding equations that you already know. Good news, you already know a couple of surfaces. Really? Yeah. Let's do it. So let's look at the two special types of surfaces that we've looked at. Well, one of them is spheres. Yeah, you looked at a sphere, and the equation for a sphere in standard form looks like this. You've seen that. And you can cherry pick off the center point coordinates. So the center point is an ordered triple here. What are the coordinates? Does anybody see what they are? Just right off the bat?
A, B, and C.
Excellent. Yeah, A, B, and C. Okay, and the radius is?
R.
Very good. Now, planes are another kind of surface. And the equation for a plane in standard form looks like this. We're going to fill in the blank on the right-hand side of the equation, and you saw this last week. Does anybody know what goes on the right-hand side here when you're in standard form?
D.
Not for standard form.
A 0?
Yes, 0. Remember, this standard form was derived from taking the dot product of two vectors, and the dot product had to be 0. That's where I derived it from. And then after you multiply everything out, of course, the plane equation looks like ax plus by plus cz equals some constant term, say d. And that's called general form, when it's all multiplied out and you got rid of all the parentheses. Okay, now when you have your plane equation, you can quickly cherry pick off the two important ingredients. What is the vector that's normal to the plane? V equals, what are the components? Remember I told you you could cherry pick it off of the equation for the plane? A, B, and C. And the ordered triple for the point contained in the plane is x naught, y naught, and z naught. You can just look at those guys here. Okay, so you now know two surfaces. Now, I'm going to have a little fun with this because, you know, I can, and I encourage you to do it too. So what am I saying? If you are working on your computer right now, and I imagine some of you are because you're Zooming, go Google up GeoGebra. So if you go to the internet, say, and you go, okay, I'm going to do like GeoGebra, and then put in 3D, 3-D, and there also, oops, put a space in between, because GeoGebra has 2D and 3D, all sorts of calculators. It's really cool. So when you go to GeoGebra, and you go like that 3D calculator, it brings you to a place where you can do some really cool 3D graphing. So, so there it is. Isn't that cool? So, well, what can you graph? Well, all sorts of things. Like, let's graph a plane. So you know that a plane equation might look like, I'm just making something up, 3x plus 2y plus 6z equals 12, just say, okay? And notice there it is. Now they have their x and y and z axes kind of pointing off in different directions, but you can kind of rotate it around a little bit. Ooh, I'm not doing too good on the rotate here. Oh boy, kind of rotate it right there. Oh, okay, let's see if I can rotate a little bit more. Oh, that's cool. Oh, that's really cool, isn't it? So the X, that's the Y. Looks like I think I want my Y down like this. Oh, this is so much fun. Anyway, it's kind of booped out. Anyway, that's good enough for government work. All right, I'm not sure if I don't think the Z is the one that's going straight up that I can tell. I'm not sure what the orientations are because they're not labeling their axes like I would want to. But anyway, so let's graph something else. How about we graph a sphere? Sure, why not? How about a sphere centered at the origin? So x squared plus y squared, and I'm using the caret key to do the square in case you're following me. Squared, I don't know, equals 9. Okay. Ooh, there we go. Look at that baby. That is a nice sphere, and it's centered at the origin of radius 3. Isn't that pretty? You guys like that? Yes, no, maybe. Pretty fun.
I have a question when it
That's
comes to
cool.
the first equation. So what's the shape for that?
It's just a flat surface. It's that green thing that's a flat surface. Can you see it?
Yeah, so can you graph a cube?
A cube?
Yeah.
Well, you would have to have the equation for a cube, and I'm not sure if I don't have that memorized. We're not going to have that as the surface. Now that would be, since a cube has 6 faces, Kobe, you could graph 6 different planes that would be all of the adjacent sides of a cube. But
Yeah.
there's no single equation to give that I know of right off the top of my head that gives a cube.
Okay.
Does that help?
Yeah.
So I'm sorry, but for now, why don't we be okay with just a flat surface, which is called a plane?
Yeah.
Okay. So, and that's a very common surface. So, you know, so you can see that green thing, it's kind of tilted at an angle, greenish. That's a plane. And you can graph more than one plane in the same problem. Like, let's get rid of the sphere and let's graph a plane like, you know, x equals 4, just for kicks and giggles. So see how that red vertical plane just happened? That tells me that the x-axis is the red one. Yeah? See how it's vertical? And you can graph like y equals 4 also. Ooh, what the heck just happened? Now, let's say I want to change colors because that's the same color as the other guy. So you could go over here and go into settings and go, oh, I want to change the color of that. Let's do purple. Yeah, that's the ticket. Okay. So if I do that, did it change it to purple? Oh, I can't tell. No, I didn't. I'll do that one more time. Come on. Why didn't you change it?
That is because you're hitting it.
Okay, so how do I select the new color? Anybody know?
Okay, close that little window. Now go back to Y and see that circle, click on it.
Oh, thank you.
You're welcome.
Okay, so that is also a vertical plane. You can kind of see that purple one straight up and down because it's parallel to the XZ plane. So you get all these planes, all sorts of them, all, you know, they're flat surfaces. Okay, so I just want you to sort of get a visual on a plane versus a sphere. They're two obviously completely different looking surfaces, right? You could get behind. But there's other really cool equations that come with other cool surfaces. So let's take a look. So one of them we're going to look at today, we're going to look at cylindrical and quadric. Cylindrical is very special, okay? Unfortunately, somebody named it cylindrical, which makes it sound like they all look like cylinders, and that's not exactly true. Although they can look like a cylinder. Aha. So what is a cylindrical surface and what is the equation that goes with it? This particular cylindrical surface has the equation x squared plus y squared equals a squared, where a would be the radius of the cylinder. So here's the official definition. The circle that is given by x squared plus y squared equals a squared is known as the generating curve for the cylinder. And so you would graph that first in the xy plane. So definition of a cylinder, let C be a curve in the plane. That would be like your generating curve. Let L be a line not in the parallel plane. And the set of all the lines that are parallel to L and intersecting the curve is known as a cylinder. Okay, and the parallel lines, they call them lines. So I'll go over this in slow motion. So the idea, though, is the equation of a cylindrical surface will be an equation that's missing one variable. It's only missing one variable. Okay, so let's do some examples. So these are some examples also, but I want to do all 3 of these in slow motion. So let's take a look. I'm going to get some extra room here. What if somebody, instead of x squared plus y squared equals a squared, let's do like, you know, an actual number. How about 9? Let's say somebody said graph that. Now, if you were in an algebra class, you would go, oh, hey, I know how to graph that. That's a circle centered at the origin of radius 3. And I would say, congratulations, that is exactly right. But that's actually the generating curve. So the generating curve is in the XY plane because the Z is missing. Now, how do you actually draw the surface? Because this is a curve, not a surface. What you do is you now draw the X, Y, and Z axes in the pointing in the directions I told you that we're going to go with, custom. And then try graphing the circle flat in the XY plane. So here in the XY coordinate plane of radius 3 and center at the origin is our curve. And now what you're going to do is you're going to whoosh it in the direction of the missing variables axes. Now, whoosh is not a technical term, okay? I had a student a few years ago who said, well, instead of whoosh, you should be saying the word extrude. And I said, well, okay, you're right. I'll extrude it, the circle in the direction parallel to the missing variables axis. So I'm whooshing this in the direction of the z-axis, and then I get the cylindrical surface, and I'm done. And I do have a cylinder. But that's not very fun because, you know, what about other cylindrical surfaces that don't look like cylinders? Aha! And we'll look at whooshing. We'll look at whooshing those, okay? So the one that was on that previous page is what about y equals x squared? Well, I hope you can appreciate, you know, you took an algebra class and you probably had to graph these parabolas in your calculus class also. So we all know what the generating curve y equals x squared would look like. It's a parabola where the vertex is at the origin, right? That's the generating curve. That's not the surface. It's what we call the generating curve. Now you have to go to 3D. Okay, so I'm going to go X, Y, Z axis. And now let's try and draw that parabola flat in the XY plane. Well, it's pointing upward in the positive y-axis direction. So there's my y equals x squared. And now try whooshing it in the direction of the missing variable, which again is z here. Now this is the part where if you're not good at graphing in 3D, oh boy, I apologize because this is going to be a little bit. So can you picture that? It kind of looks like a curved piece of paper, if you will. You know, I can maybe draw a portion of it. It would look like this. Oh man, this is not doing too good. Okay, so it kind of looks like that. All right. It's not a cylinder, but that is known as a cylindrical surface. Okay. Looks like a curved piece of paper. So if you can see my video, it would look like this. It's like a piece of paper kind of curved around like that. Kind of cool. It's a nice surface. Okay, the other one is also a parabola. Let's take a look at that. What about y?
Excuse me, what if you added what if you added z squared to the parabola? Would it
Well,
look like a satellite?
Oh, well, you can't just add the z squared in because the equation was y equals x squared. Are you saying you want it to look like y equals x squared plus z squared?
It's like I was wondering if you could do like both parabolas simultaneously between y and x and y and z.
Well, you could always graph more than one surface at the same time. Sure. I mean, if you wanted to graph, say, y equals negative x squared, like this, yeah. And then you'd graph both of these. Let's see if I can do it with a different color. This is going to be fun. Oh my goodness. So if I graph the y equals negative x squared, and then I whoosh that one in the direction of the missing variable. Oh boy, this is not going to go well. I don't know if you can tell what I'm doing here. Can you kind of see that, what I'm doing? Anyway, you can graph more than one surface at the same time. I don't know if that helps answer your question, but let's continue on. And if you still have more questions at the end, we'll revisit that. I'd like to do y equals z squared now. How would you graph y equals z squared? This is a little bit trickier for a lot of students because you're no longer in the xy plane. Because the x variable is missing, you're going to be whooshing when you do the whooshing in the direction parallel to the x-axis. But first you have to draw the generating curve. The generating curve is no longer going to be in the xy coordinate plane. It's going to be in the yz coordinate plane. And because y can be considered normally the way it's written here, it looks like, well, y is the independent variable. Yeah, but you're graphing y equals z squared. So it's going to be a horizontal parabola opening up to the right. This is the generating curve. It's in the YZ plane. Okay, I know you're going to probably get turned around when I do this, but try to stay with me here. So when I go to 3D and I draw the generating curve in the YZ plane, remember the YZ plane is like right here. Okay, so you're going to draw this opening up to the positive y-axis parabola like this. Okay, here he is. And then you're going to whoosh him, whoosh being the operative term there, in the direction of the x-axis. And this is kind of where it gets a little bit like, oh, I'm not good at 3D. Yeah, welcome to my world. I had to spend years trying to figure out how to draw this. And it also looks like a sideways turn piece of paper. Now I don't do that well drawing, so this is a better drawing of that, better than I did. And then this is the picture of the other one, a little bit better than I did. But I think you get the idea that the rulings, those lines, are parallel to the missing variables axis. Okay, that's the key. So you guys want to try a couple on your own? Okay, so we graphed our generating curve, and then we graphed our portion of the sine curve in 3D, but it looks pretty gross. So we're going to try and go to GeoGebra. Let's delete a couple of these other guys. Let's just get this one guy here. Let's do a different equation one here. Let's do, oops. So let's do z equals sine x, and ooh, now see, that's a nicer picture than I'm doing. Okay, so I hope you can appreciate that. That looks kind of pretty, actually, doesn't it? That's a cylindrical surface. I know it doesn't look like a cylinder.
I
but
can't
that's
see
why
it.
Yeah, are you supposed to share your
I'm
screen?
not sharing.
It's just sharing the PDF.
Oh, I know why. Sorry. How about that? Can you see the whole screen now?
Perfect. Yep.
Yeah.
Yeah, so can you see that this looks a lot prettier than my drawing? I'm just trying to rotate it in different angles here. I'm not having much luck. So it's that's called a cylindrical surface, even though it doesn't look like a cylinder. And the reason why is because it's missing that one variable. That's kind of pretty. And now if we go to the letter B, if you had luck doing y squared plus z squared equals 4, first do the generating curve, and that would be a circle in the YZ plane, and it's a circle centered at the origin of radius 2. So there's the circle, but then here in 3D, you graph your generating curve in the YZ plane. So I'm going to try to draw my circle here, the radius 2, and it's kind of like a vertical circle here. And then I whoosh it in the direction of the missing variable. That would be x. And then I'll get a sideways cylinder. So that looks pretty bad. Yeah, that other one does look like a sun chip. I would agree with you. Yeah. So now it's like, okay, that looks pretty bad. So if you did want to go to GeoGebra, and let's delete this one. Let's start over. If we did y squared, oops, y squared plus z squared equals for, there we go. So it is a cylinder on its side. And their y-axis is pointing in the wrong direction for me, but at least you kind of get a feel for what this thing kind of looks like. Yeah, pretty cool. So that's cylindrical surfaces. Congratulations. I think that we covered cylindrical surfaces in enough detail now for you to be on your own. Let's do a different kind of surface now. Let's do quadric surfaces. So there's another kind of surface. By the way, these surfaces that we're studying right now, there's millions, infinity kind of surfaces. We're just studying some classic ones with their classic equations, okay? So a quadric surface is a second degree equation. That means that you won't have anything higher than a power of 2, okay? Power of 2, power of 1 is okay, but nothing higher than a power of 2. Now, if everything is a power of 1, that means you have a plane, okay? You know, x plus y plus 2z equals 7. All the x's, y, z's are raised to the 1 power. That's automatically going to be a plane equation. That's not really considered a quadric, okay? Not traditionally. But you might have an x squared term, might have a y squared, a z squared, then you might have an xy term, an xz term, and a yz term. And then you'll have a plane x, a plane y, a plane z term, and then you'll have a constant term. Or not. The constant could be 0. I don't know. And there's 6 basic types of quadrics that I'd like you to know for this entire course. And they're listed all here. I'm not asking you to memorize them because I certainly don't have them memorized. But we're going to just look at a few, and then we're going to talk about the trace of a surface. Now, when we talked about traces when we were doing planes, it's basically the curve that that surface gives when it intersects one of the coordinate planes. And the way you can figure it out is by setting one of the variables equal to 0. And then you can see the trace in that coordinate plane that you're looking at, okay? So the traces of quadric surfaces are conics. And if you remember conics you studied in a pre-calc class, that consists of circles, parabolas, ellipses, and hyperbolas. Those are what the traces of quadric surfaces will look like. It'll be relegated to those, okay? And you can think of quadrics as the 3D analog to conics, because they are. So here's all the different kinds of quadric surfaces. Ellipsoids, I like to think of as ellipsoid as a 3D ellipse, because it kind of looks like one. It looks like an egg. If A and B and C are all the same number, you'll get a sphere instead of an ellipsoid. So it's almost the sphere equation that they rearranged, okay? And if you look at the trace of an ellipsoid in the z plane, you would set z equal to 0, excuse me, in the xy plane, you'd set z equal to 0 to see what the trace is in the xy plane. And that would look like an ellipse, as it like these red things that they show here on my slide here are the traces. And you get a sphere when A and B and C are all equivalent, not 0. A hyperboloid of one sheet. Oh my God, it almost looks like an ellipsoid equation, but do you see the one difference? Why don't you compare this?
The negative.
Yeah, one of the terms will be negative. Will it always be the z? No. If it is the z that has the negative in front, that means the hyperboloid of one sheet is going to be parallel to the z-axis. If it were the x squared term, it would be thrown over on its side. Hyperboloid of 2 sheets. It kind of looks like a one sheet where somebody snipped it in the middle. And you'll notice that it almost looks like the ellipsoid because it's got the 1 there on the right-hand side of the equation, except you have 2 negatives now, 2 negative terms. The other 3 are elliptic cones. So you again have 1 negative, except notice here, this is a 0 now, not a 1. If you have a 0 for your constant term, you'll get this elliptic cone, which is centered at the origin. And it looks like 2 ice cream cones stuck together, doesn't it? Yep. Elliptic paraboloid. I love these because they kind of look like a parabola that's in 3D. And you have 2 terms that are squared and one of them is not squared. That's how you tell you have a paraboloid. And you know that when you have a parabola, just a little review here, a parabola like y equals x squared, one of the terms there is squared and the other one isn't. Sort of like the elliptic paraboloid. And then finally, the hyperbolic paraboloid, where one of the terms is not squared, the other two are, and they're on the other side of the equation, but one of them is negative. Okay, and that kind of looks like a horse's saddle to me. Doesn't this kind of look like a horse's saddle to you? Like, look, like I can draw a horse right here. Yeah, that's right. He's got a saddle on him, right? You see that? See my horse? I know, that's pretty pathetic. Okay, sorry. Yeah.
It's like a badly made potato chip.
It could be a bad Pringles potato chip or something. I don't know. Okay, let's do one sketch of a quadric surface and try to figure out what it is. Now, certainly you could go into GeoGebra and pound this out and have it just sketch it for you. Of course, that's an easy way. But let's say you had to do it without your GeoGebra and let's answer some questions about what the traces would be. The traces would be the intersection curves with the coordinate planes. Okay, fine. First up, this equation doesn't look like anything on the previous couple pages. Like, I can't match it to one of those quadrics there. How am I going to match it? So the idea is you try to match it. You do your best. So first, I notice there's a constant term of 12. So I'm going to subtract 12 from both sides of the equation to get the constant term on one side. And then, well, what do I have now? I've got all these terms on the left, which is kind of a big mess. And remember on the previous page, if we did have x squared, y squared, and z squared terms, then this on the right-hand side had to either be a 0 or a 1. Well, we can't turn it into a 0. So we're going to assume that we need this to be a 1 to match one of those standard equations. And so what am I going to do? I'm going to divide both sides of the equation by negative 12. So then, after dividing both sides of the equation by negative 12 and distributing my negative 12 over all three of the terms there in the numerator, and then reducing to lowest terms, and watch out because I got a lot of minus signs running around here. The first term would be negative x squared over 3. And then this other term, the next term, there's a minus minus, so you could just change that to a plus y squared over 4. And then the minus here, you can bring it over so it's just sitting in front, minus z squared over 1 is equal to 1. And now this looks like it's in standard format. So does this match any of the 6 choices on the previous page, where you've got a 1 on the right-hand side, and it looks like 2.
Well, I can say the XY plane will probably look like a ellipses, right?
Well, you got to be careful here because you want 2 of the terms to have a negative in front of them. You notice here I've got a negative in front of the x squared term and a negative in front of the z squared. So
Yes.
it won't be an ellipsoid. Ellipsoids like to have all of their x squared, y squared, z squareds positive. Like check out that ellipsoid, that egg at the tippy top. Do you see his standard equation has everybody with a plus?
I see.
So is there something else where we have 2 negatives?
Yeah, it's hyper.
It's that guy. Now, it's not exactly that guy because the negatives that we have are not the same. Like this one that they're showing has the negatives in front of the x squared and the y squared term. Ours has the negative in front of the x squared and the z squared term. So what is our guy going to look like? And it's on the, if you go to the next page, there's the graph of it right here. Now, what about the traces? Like, how do you get traces? So if you look here, to get the XY plane trace, set z equal to 0. And that means that the trace will look like a hyperbola in the XY plane. And that's sort of true. Like if you look here where it intersects the XY plane, you get, you know, essentially a hyperbola. If you look at the XZ trace and you set y equal to 0, you get that equation. But this equation is impossible. Why is it impossible? You can't get the sum of 2 squared terms equal to a negative number. That just can't happen. So you don't have a trace. It never intersects the XZ plane. Oh, okay, good, fine, you're done. How about the YZ trace? Well, when you set x equal to 0, you get that equation, and that would be graphed as a hyperbola in the YZ plane. And then we have Pringles are examples of hyperbolic paraboloids. Okay, so I'm done with this section, and here's a little warning. You don't know every single surface in the universe because there's infinitely many kinds of surfaces out there, all sorts. Here's some pictures of some really bizarre looking ones for you, just for fun.